Hey, we're here to go over some qualitative examples of Newton's second law where we're solving for expressions and things like that. So let's get started. Just a couple things to cover before we actually get to the problems, and that's just mainly this is our first time dealing with a qualitative problem. And so all qualitative really means here is that if we're dealing with concept stuff, then that means the answer is purely conceptual. You want to talk about like as some things go up, what else goes down, right? Just kind of like broad stroke ways of talking about a concept. And then when we're doing things with equations like we're going to be doing today, something that's qualitative means we're not ever going to be plugging any numbers in. We're only going to be dealing with the variables. So a really common thing that happens on the AP exam is we have to solve for a variable, and we call that by solving an expression, okay? The other real important thing to remember here is the force of gravity equation, okay? Also known as weight. And so just so we're all on the same page, we're all starting off on the same page, just remember the force of gravity is a really quick and easy equation, but that is the mass of an object times the pull of gravity. And so what this is this is the weight right here, F of G, force of gravity, and this is an object's mass, and this is the what we call the gravitational pull strength. It's the acceleration of gravity, right? So this is generally 9.8. And when we're talking about the pull of gravity, usually we would say newtons per kilogram. So it's going to pull with a force of 9.8 newtons on every kilogram of mass. Okay? If you work out these units, you'll see it's the exact same thing as saying 9.8 meters per second squared. Okay, and you can watch the previous video we have on the units and everything with Newton's second law and forces, but you can see how those units work out. Okay, so 9.8. But like I said, today is going to be qualitative, so we don't even really need to worry about that number right now. Okay, so let's get into it. Very first problem, we have a helicopter of mass m, and it's taking off and accelerating upward. So we want to solve for the expression of the helicopter's lift force. So here is this wonderful drawing that has been provided by a just world-renowned artist. And we, just like before, we want to set up our free body diagram to be able to look at the forces and everything going on. So in order to do that, I'm going to say, all right, you know, I got my little imaginary dotted line around the helicopter. What are my contact forces? And my contact would be, I have the air is pushing up on my helicopter with a lift force. We'll call it lift. And that is really all that's touching the helicopter. Okay, so now I go and draw my free body diagram. So I know it's accelerating upwards. So my up force needs to be more than any of my down forces. So the force of gravity on this, the long range force, will be just a little bit smaller. Okay. And now you're going to see why Newton's first law comes into play, because I know everything is accelerating upward. So that tells me there is a net force in the up direction, right? So the vertical direction. So when I set up, remember, I always want to look at things horizontally and vertically. So I'm going to say, okay, I know that there is no net force in the x direction. So I can set that equal to 0. In the y direction, I know that I can actually set up Newton's second law, boop, boop, and get ready to solve for this. Okay, so I have the net force in the y direction is equal to the mass of the helicopter times the acceleration in the y direction. And from here, now it just becomes time to use this equation and isolate the lift force. So let's say, figure out what is the net force. Well, the net force is the force of lift. So I'm going to look at my free body diagram, and I'm going to use that to figure out what my net force is, right? The one going up in the positive direction, that's going to be positive. So I have force of lift. And remember, it's a net force, so we add everything. So plus, and then this force of gravity is negative because it's pointing in the downward direction. So I say plus negative force of gravity. And that's equal to, those are my only forces, so that's my net force, and that's mass times acceleration in the y. Okay? And we were being asked solve for the lift force, so I want to get this variable all by itself. And so I'm going to do just one little bit. Remember, we know how to plug in this force of gravity equation. So I'm going to say F lift. Now plus and minus together right there make a negative, so that's minus. And mg is our equation for the force of gravity. Equals mass times acceleration. And the last bit I need to do is get this force of lift all alone, so I can add mg to the other side. Right? Those are going to cancel out, and I'm left with force of lift is equal to mass times acceleration plus mass times the pull of gravity. And there is, if you notice, we'll just kind of mathematically, there's one little thing we can do here. And there is a common mass in each of those terms, so we can actually just factor out that mass and make it look a lot nicer. Boom. Okay. So we figured out what is Newton's second law in each direction, and then used that in our knowledge of what direction the acceleration is to set up our problem. Okay? Cool. All right, let's do another one. A student of mass m, so a lot of these are going to be mass m, right? A student of mass m stands in an elevator as the elevator accelerates downward. Solve for the expression of the acceleration of the student. Okay, so I'm solving for acceleration this time, but nothing in my process changes. So first I need to figure out forces. So the student, the only thing in contact with the student is the floor of the elevator. So the floor is pushing up on the student with a normal force, making sure that the student doesn't go falling through the elevator. And that's the only thing in contact with the student, right? So when I draw my force diagram, free body diagram, sorry, I have the weight of the student, called the force of gravity, and then the normal force. And I know from, what does it say? It's accelerating downward. So I know that there needs to be a net force going down, right? So the normal force, if that's the only other force around, it needs to be smaller than the weight so that the net force is going down. Okay? And so now I start setting up Newton's second law, right? I know there's no forces in the x direction. There's no acceleration in the x direction. So that lets me know that the net force in the x is equal to 0. And the net force in the y direction is equal to mass times acceleration in the y. So I'm going to start here and plug in my forces in the y direction using that free body diagram. So first is always the thing that is positive, right? So I have positive normal force plus, and then we're adding everything, and this force of gravity right here is going down, so it's going to be negative. And that's equal to mass times acceleration in the y direction. Okay, so all of these forces and accelerations and all of those quantities are now in the y direction. I'm dealing only in the y direction. And we were told solve for this acceleration in the y. So that's what I'm trying to get all alone. So I'm going to plug in my mg for the force of gravity. Right, and now I can divide both sides by this mass to get rid of it. So that would give me normal force minus mg all over m is equal to acceleration in the y. And this is a final answer, but then depending on how, like maybe it's a multiple choice question, maybe free response, it's not too big of a deal, but it could look different in the multiple choice. So let's simplify this just to be sure. So I can split this if I have a mass in the denominator and there's just that one term in the denominator down there, then that means this is now like a little bit of math. That denominator can get split up between every term in the numerator. Right? And now take a look at what happens. If we have this, right, normal force over mass, you can't really do anything there. But here I got a mass on top. Let me get the right color. Da, da, da. Let's see. One little thing. Let's get this. Right, mass on top cancels with mass on bottom, and then we'd be left with normal force over mass minus, and then you just have a G left there. So that could be like final super simplified answer. Or if this is like a free response where simplifying doesn't matter, right, you could do that first one up top. So either one. Alrighty. Moving on. All right, we have a kid of mass M is pushing horizontally on a fridge in a desperate attempt to move it across the room, but it just won't budge. So we know they're pushing horizontally. Give me my pen. Pushing horizontally. Okay, so I know this kid, so if we're drawing a free body diagram for the fridge, I'm looking at the fridge and thinking, okay, what things are in contact with the fridge? So I know there's this kid pushing on the fridge to the right. We'll just call it F push, why not? All right. I know that the fridge is actually in contact with the ground. And so the ground is pushing up on the fridge with a normal force, making sure that the fridge doesn't fall through the ground. And even though the kid's pushing on it, the fridge is not moving. So I also know that there's some friction force that is pushing on the fridge. And that also comes from the ground, and that's parallel to the ground to make sure that the fridge doesn't move. And so you notice looking at that free body diagram, that's kind of like there's stuff everywhere. So now you're seeing why we draw free body diagrams. Right? I have a normal force going straight up. I have a push force going horizontally to the right. I have a friction force to the left, which is resisting the fridge actually sliding. And then I have the force of gravity going down. Okay. So notice it says that it will not budge. That tells me that the velocity is 0. And that also means if the velocity is staying 0, it's constant, that means the acceleration is 0. So in the thinking about like Newton's first law and what that tells me, that means that in each direction, the x direction and the y direction, the net force is 0. All of these forces are canceling each other out. That means I got just as much going up as I do down. So I could put even a little tick mark on it to show that. And then however hard the kid is pushing, friction must be resisting the exact same amount. Okay, so let's take a look, and the push, and what is it? We want to know an expression for the friction force, right? Well, the friction force here is in the x direction. So I'm going to first start in the x direction to see if I can solve for it. Okay, so I'm going to say the net force in the x direction is equal to 0. So what is my net force? When I add all my forces together? Well, I got to push to the right. So that will be my positive force, because to the right is in the positive direction, plus negative force of friction. And it's negative because it's in the opposite direction to the left. And that is equal to 0. And now our whole goal is just get that one friction force isolated, which is pretty easy. All right, I just get them on opposite sides of the equal sign. So that is saying that the friction force here is the exact same magnitude of however hard the kid is pushing. And that's why the fridge actually isn't moving. Okay. All right, a couple more. We got a 4-engine rocket car of mass, capital M now, and it's speeding up as it moves to the right. So speeding up automatically starts letting me know that, okay, this thing is accelerating and to the right. All right. So make an expression for the thrust force produced by one of the engines. Okay. So let's figure out all of our contact forces, right? We got the ground holding up the car with a normal force that is perpendicular to the ground. I'm going to have some form of friction on these wheels. Okay, and then each of these engines is responsible for applying some thrust force. Okay, so let's call it FTH. So I'm gonna, same thing for all of these. FTH, FTH, TH for thrust. Okay. And that looks like all of our contact forces. So when we draw the free body diagram here, I have the normal force. Okay, I have 4 of these thrust forces. So there's a couple ways you could go about this. FTH, 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 FTH. Okay, I have a friction force. I know right off the bat that I don't need to draw this friction force as long as the thrust forces, because this thing is accelerating to the right. So there needs to be more force to the right than to the left. And then I have a force of gravity going down. Okay. So in the X and Y direction, let's think about our forces. Newton's first law lets me know, well, in the Y direction, there is 0 net force because there's no acceleration up or down. In the X direction, there is an acceleration. So what we need to do now is basically take our X direction, Newton's second law, and fill it out. So we have, let's go in the X direction. Anything pointing to the right is positive. Anything pointing to the left, negative. So I have FTH plus FTH. So all 4 of my thrust forces plus negative force of friction. And that's equal to mass times acceleration in the X direction. I'm going to scoot it over just a little bit. Okay, from here I need to now solve for the thrust force of one of these engines. So I just need to solve for FTH. So watch what happens. I have 4 of the exact same thing. So just like any normal math, 4 FTHs minus the force of friction is equal to mass times acceleration in the X. Okay, now my goal is, again, get this FTH variable all by itself. So I need to start getting things to the other side of the equal sign. So I'm going to add force of friction over to the other side. So I have MA in the X direction plus force of friction. Okay, then the last thing I need to do is I'm going to divide both sides by 4 to get that 4 out of there, and that would be 1 over 4. Boom. Okay, there's nothing else I can really do to simplify that. I don't have any good expression for friction force. MA is fine right there. All right, so that is a qualitative answer for the thrust force produced by one of those engines. And we're back. Had to do a little frantic reorganizing of the computer because I ran out of storage space right as they finished our last example. And one thing that I remembered is in all of these places that I use mass, originally it said the mass was capital M. So that's just one, and it's a silly thing, but all of these places where I wrote mass, we could go back and put capital M if we wanted this to be purely accurate with the values that were given to us. So big M for mass times acceleration. Okay, changes nothing about any of the problem that we did. It just changes the variable that we used. All right, we got one more that we can go over, and this is for a girl of mass lowercase m, and she's jumping on a trampoline. When she's at the deepest part of this stretch for the trampoline, she begins to accelerate upward. So already I'm like, okay, all right, accelerating upward. I know there's going to be a net force in the y direction. Solve for an expression for the girl's mass. So we're going to be solving for her mass. So right away I'm going, all right, I need to put the contact forces on her, right? So really the only thing that she's touching, her legs are touching the trampoline. So there's a normal force from the trampoline actually like stretching down and pushing up on her. And so when we draw this free body diagram, I have her weight, which is Fg, going down. That's the long range force. And then I have the normal force going up. And again, just qualitatively, I know that this vector right here should be bigger than the weight vector because her net force needs to be going up. So right away, I know the forces going up need to be bigger than the forces going down. Okay. And all right, so let's set this up. In the x direction, I know that there is no acceleration and no net force, because Newton's first law tells me anything accelerating needs to have a net force in that direction. So there's no horizontal forces, so that takes it out. In the y direction, we look at mass times acceleration in the y, and there is a net force here, so I'm going to now fill in what the net force actually is. The net force is whatever's going up, so let's go white. Normal force plus, and then this force of gravity down here is pointing down, so that's going to give it a negative force of gravity. And that's times mass, or equal to mass times acceleration in the y direction. And then what are we solving for? For her mass. So I am trying to get that variable m all by itself. So that's just one step that we need to do. Let's see, normal force minus, remember we can turn Fg right there into, we can replace it with its equation for the weight. That's just mass times the pull of gravity. And all of this is going to be divided by the acceleration in the y direction. Right? If I wanted to get that mass all alone, then I would divide both sides by, not mass, silly Cunningham, I would divide both sides by a. Right? And I'd be left with mass on that side. So it doesn't look like there's a whole lot I can do to simplify any of this. There's no expressions I can substitute in for normal force. There's nothing I can really plug in here. But you know what? This actually isn't solved all the way for mass, because take a look. I have mass on both sides of this equation. So we're going to need to actually fumble around with this a little bit. So I'm going to, and you guys are coming along on this journey with me. This is, of course, the one problem I wrote and didn't work out ahead of time. So let's say, all right, this last step, erase it. I'm going to go back up to here. Okay, so I'm actually going to erase it now. If I can, my thing's being weird. Do the little Maybe. I just want to erase stuff, you know? There it is. Wait. Hey, okay. Bum, 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 ba-dum. All right. So let's plug in our expression for the weight, mg. And I know I need to get m by itself. So the only way I'm going to do that is by getting everything, every term with a mass in it to the same side so I can then factor it out. So let's get this mg, let's get this mg right here to the other side. So I'm going to add mg to both sides. Right? These mg's will cancel out, and so I'm left with normal force is equal to mass times acceleration in the y plus mass times pull of gravity. Okay? Now notice what we can do. Why did we get everything to the same side with an m in it? Because now I can factor out this m. And I can finally solve for mass. So I'm going to divide both sides by acceleration in the y direction plus g. Right? This whole little expression right there will cancel out. And so I'm left with, as a final qualitative answer, mass is equal to the normal force divided by A plus G. All that work to get this nice, pretty, simple little answer. All right, so if we knew, the reason why this is nice now is if we knew these values, if I knew what the normal force was, G is always 9.8. And if I knew at what rate she was accelerating, maybe by using kinematics, then I would be able to actually figure out what the answer to her mass is, right? But right now, it's just all variables. So yeah, these are all the qualitative examples. We'll do more in class and everything, but if you have any questions, feel free to hit me up, and I will talk to you later.